Alaikum and good day. Today we're going to discuss about Verilog HDL. So you guys have been working on your lab exercises and tasks. So you have been through uh, a lot of Verilog's coding, and then by now I think at least you guys have the basic idea of what Verilog is and how it is functioning. Right, so today I'm going to share with you guys some of this basic knowledge that you guys need to know regarding Verilog HDL. Right, so today's lecture objective is that you guys will understand about the hardware description language. It's a better design entry method than schematic entry. So this is something that we're going to prove throughout this lecture. We're going to compare how HDL helps the designer to design, to make their design job easier. And then the basic structure, we're going to discuss about the basic structure of a module specified in Verilog HDL. So by the end of this lecture, at least you guys have an idea how the basic structure of a module in a Verilog, and then what are the common syntax that being used in Verilog, and then what are the differences between continuous and procedural assignments. So by the end of this lecture, at least you guys understand and know what is continuous and what is the procedural assignments, and then what are these always block means in the Verilog, and then sensitivity list, and also nets and versus variables. All right, so basically these are the basic comparison that we can have between schematic and also HDL. So the schematic, if you guys remember, is what you did in your first lab. So you guys are using this block diagram, AND gate, dropping it on this schematic and developing the circuit through connecting the lines between the gates, right? So basically, I mean, it is good for multiple data flow. You guys can see this data flow, and then it's giving you a good overview picture. You can see how the gates being connected, and it is really relate to the hardware. So I mean, when you are working on the hardware, you can see the gates. You know that it's being connected by the wire. So I mean, it is really relate to the real hardware, and then you don't really need programming skills. So you just need to drag and drop and do the connection, and high information density, and then I mean, it's easy to name for the naming and everything, and it's useful for mixed analog and digital signal because you can see the circuit combination, right? But the disadvantage of using schematic is that it's not good for algorithms, because I mean, it's hard to to design algorithms by using the gate, and then it's not good for data paths. It's gonna be really complicated, and then poor interface to optimize, difficult to use. So these are the disadvantages that you can have by using this schematic design. Okay, then we look into this HDL, hardware description language. So it is flexible, and then it's excellent. So it's easy to optimize and synthesize. It's a direct mapping to algorithms. So it is easier because it is more closer to this software programming language. So it's easier for the designer to transform their algorithms into this coding of this hardware coding, and then excellent for data paths. It's easy to handle electronically, right? So it's only need text editor. You don't have to have a circuit or whatsoever. So the disadvantage is serial representation may not show overall picture. Of course, you don't see the overall picture because it's a coding. Unless you compile it, then you can go and look into how the circuit being implemented on the FPGA. And then of course you need to have a good programming skills. Okay, so the HDL is not something that related to the physical hardware. So the learning curve is quite steep. So you're going to take a while, to really get a grip on this HDL language. But don't worry, if you guys keep on doing it by yourself, I'm pretty sure by the end of the semester, you guys will be good at Verilog programming. Right, so Verilog HDL. Why this industry moving towards Verilog? I mean, if you guys going into the industry nowadays, I mean, when you mentioning about digital design, now people will talk about HDL, Verilog, system Verilog, VHDL. So there are no more this, gate level design. So because it is something that being adapted by the industry, and nowadays, I mean, they are using this programming language, to ease the design work. So why Verilog or HDL becomes, favorable to the industry? Because it is similar to the C language. So it's easier for the engineer, to work on it, because I mean they have the basic of C language of programming. So same as you guys, if you guys have a good programming language, then you guys can get the basic concept easily. So, but it might take a while to develop the skill in the programming for Verilog. Right, so basically there are three different levels of description that we can look into Verilog. So they have behavioral level, register transfer level, and also gate level. So basically, gate level is the one that you guys been doing for your first lab. So you guys are directly using AND gate, OR gate, NAND gate, right? And then the register transfer level is the one that you guys been using for lab 2 onwards. Mostly is register transfer level. Behavioral level we're gonna cover might be later. This most of the time you're gonna use behavioral level for this manual simulation, right? When we want to write the test bench code, then we're gonna use behavioral level. So it's not just a specification of the language, it's also associated with the simulation environment. So as you guys know, I mean, this is a circuit. We are programming a circuit. So when we program a circuit, we need to test the circuit, right? So to test the circuit, we need to write, I mean, like if you guys go into the advanced level, you guys need to write your own code, to test the circuitry that you guys have designed. And then Verilog HDL is easier to learn. It's a lighter weight compared to its VHDL, but I think it's, I mean, both ways okay. Both language are pretty, that easy to learn, but each of the language have their own advantages, and then it's a very popular with the chip designers. So basically, in this lecture, we're gonna use two examples. So the first one is 2-to-1 multiplexer, and the second one is the 7-segment decoder. So this is structure of a module. So we're going to discuss about the structure of a module. So basically, if you guys look here, the block diagram, I think you guys can notice this is a multiplexer, right? So we know that this is a 2-to-1 multiplexer. We have 2 input to the multiplexer and 1 output from the multiplexer. So now from this block diagram, how we can specify it by using this Verilog, right? So the first one is that, of course, we need to start with the module name, right? So in this case, you guys can give whatever name that you want to give, but I think it's easier to give a name that you can understand, and also other people that looking at your code will understand, right? So give the name. So you have to remember that in giving a name, you cannot start it with a number, symbols, whatever. You need to start from a letter like A until Z. All right. So and then you should have it shouldn't contain any space between the name, right? And then we need to have a bracket. So in this bracket, we are specifying the input and also the output, right? The input and also the output from the circuit that we want to develop. So in this case, we have out bar, which are the output, and also A, B, and also select as the input. All right, then we specify it. So you have to close bracket, and then don't forget to have this comma here. Okay, so the output in this case is out and out bar, and then we have to specify the input, which is A, B, and also select. All right, so basically this is just a box, right? So basically we just define a box like this, right? So we have the inputs, three inputs, right? A, B, and also select, and then we specify the output, out, and also the out bar, right? So we don't have anything inside here. So how we gonna design what is inside the circuit is by looking at this part here. All right, so here we're talking about express modules behavior. So what is meant here is that how we determine the output of our circuit. Right? So the output of our circuit is that it is based on select, right? So in this example, select is only one bit, right? So we are using option here. If select is equal to 1, then out will be equal to A. If select is equal to 0, then the output will be equal to B. This is fixed, right? Whenever you are using this kind of symbol, I mean this question mark, so I mean if it's correct, the condition is correct, which is 1, then A will be assigned to out. If it is 0, then B going to be assigned to out. So that's why we can see in the truth table here, if select is equal to 0, the out going to be equal to B. If select is equal to 1, then out going to be assigned to A. All right, and then assign out bar is equal to, I mean this symbol here is just inverted of the out. So if the out is equal to 1, then you invert 1, then out bar going to be equal to 0. Right, so we're going to discuss about continuous assignment. What is meant by continuous assignment? So continuous assignment is being used to describe combinational logic. So the right hand expression continuously evaluated. So the right hand, so example here, the right hand expression here will be always evaluated. It's not depend on any system. I mean, whenever select change, right? So automatically the out will be assigned to respective value. Without any any additional signals to be assigned with, right? So for an example, let's say select is 1, then automatically A gonna be assigned to out. So if select is equal to 0, then automatically it will be assigned to out, gonna be assigned to B. Right, so left side must be a scalar net or concatenation of net. So basically on the left hand side here, I mean it should be a net. So we're going to discuss about it later, right? If you can see here, we don't specify the type of this output. So basically if we don't specify, by default it's a net. Right? So all continuous assignment execute in parallel. So it's not being executed in sequence. So it's gonna be in parallel. So if you guys change, I mean it's like a circuit. So it's, I mean this is how the circuit. Sorry, this is additional circuit. So the circuit looks like this. So every time you have the changes, then automatically the output will reflect to it, right? So it's being execute in parallel, not in sequence in the software. It's not that it's going to execute this one first, the line, first line first here, and then after finish executing the first line, it's going to execute second line. No, it's not going to be like that. It's going to be execute both lines at the same time, simultaneously or in parallel. Alright, so all continuous assignments execute in parallel, and then the operators in expressions are low level. So, for example, the question is conditional assignment. So, if the condition is true, then select the first one. If a false, select the second one. And you can also use the Boolean, inverted AND, or so you can also use arithmetic. So, operators can be nested. For example, here is 4 to 1 marks. So we can see here there's a condition within a condition. right? We can see there's a condition here, S0. If S0 is true, then select I3. If no, select I2. And then this condition is within another condition, which is for the S1, right? This is what we call as nested. And then this is how the diagram looks like. And then this is how the coding looks like, right? So for example here, S0, I3 or I2. So it's I3 and I2, and then it's depend on S0. If S0 is 1, then it's going to be selecting I2. Then I2 going to go into 1 here. Then after that, it's going to select here S1. If 1, then it's going to select the input from the marks here. Right. Okay, so the other thing is about description at gate level. So I think this one you guys have covered in lab 1. So you guys have done it and submitted the lab 1, right? So this is basically how you guys doing the coding at the gate level. So example here not represent not gate, and represent AND gate, and then you can have multiples of AND gate but having a different name here. So you can have like 10 AND gates and you can name it differently, A1, A2, but you cannot have a similar name here. So it has to be a unique name. So A1, A2 up until A10, right? And then yeah, this is how the circuitry looks like. Based on the connection that you guys create in this Verilog, then this is how the circuit diagram looks like. For example, here you can see AND gate, right? So A1 here. So the input to A1 is A and also select A and select, and then the output is out 1. And then AND A2, the output is out 2, and then the input is B and cell B, B and cell B. And there's a NOT I1, so the input is cell select, and then the output is select B. And you can just follow the code here and look at the how it looks in the circuitry. All right, so now we're going to discuss about procedural assignment using always. So procedural keywords always and initial are used to define procedural assignment. So if you guys look into what is the procedural assignment means in software, so it's like a condition, right? So it's a good for behavioral description of hardware, including combinational and also sequential logic. And then as you guys can see here, there's a always condition here. So always, and then there's an at, and then in bracket. So these are the signals that you want the coding to be sensitive with. So always, if there is any changes in the signal A or B or select, then it will update the value, right? And then so within the always itself, you can put a lot of condition. So it looks looks like more towards C programming, right? So you can use if, for, while, and also case. So normally assignment inside an always block. So assignment inside within the always block must be declared as variable data type such as register. So if you guys want to have a variable inside the always condition, it has to be a register. For example here, out and out bar, out bar, so the output, right? So it has to be a register type, which is you declare it as reg. And then statement inside the always block are executed sequentially. So okay, previously we talked about the assign, right? So the assign, we said it is being executed in parallel. But in this case, when something that you put in always function, right? So it will be executed sequentially, right? So for example, it's gonna execute the first line here first, if select. Then if it's not, the condition is not true, then go to else here. All right. So order matters. So you really have to take consideration of the order, which one you want to be executed first, like in software. Finally, you have to note that when you are using always, then you have to have begin and end. So I mean, all the conditions that you want to execute in sequence will be within the begin and also end. Okay, so this is just letting us know that Verilog register, if we declare as a register, is not exactly the same as the digital register that we learn in a class, where you need to have a clock that will affect the changes of this the register. So it is more into stating that this variables register is something that can hold a value. So that is just something that we need to know about Verilog register. So it's not exactly like the register that we learn in theory. So it's just a variable that can hold a value. Right. And normally in a design, I mean, of course, we're going to mix the procedural and continuous assignments. And it is okay to do that. For an example here, so this is also again this amount example, right? So first is we are using procedure description, right? So always either A, B, or select. If there are changes in either one of these three signals, then begin, right? So they're going to check the condition. A select is equal to, if the condition is correct, then output going to be assigned to A. Else, if equal to 0, then out equal to B, right? This procedure, because it will be run in sequence. First line first, then goes to second line. And then we also are using this continuous description. So for example, we are assigning the output, the out bar equal to the inverted of the out, right? So as you can see, a sign here is a continuous. It's always be like that. I mean, it does not depend on the changes on A, B, or select. Case statement. So you guys also have used the case statement for the JK flip-flop, right? So as you can see, case is how you can select which output that you want to pick, right? For example here. So this is also developing these 2-to-1 marks, and then for the case here, so case and then the bracket select. Of course, I mean, you start with always, right? Because this is a procedural method. So start with always, then put all the input that you want to be sensitive of, and then start with begin, and then case, right? Case in bracket, select, because now we're just focusing on select input. So if select is equal to 0, then output will be equal to B. If select is equal to 1, then output is equal to A. Then end case, then end begin. All right, so end case should have a special end to close the case. All right, and for the numbering notation for numbers, so there are different methods you can use to assign number in Verilog. For an example, you can assign using 2-bit binary. Binary. So in this case, it's a 2-bit binary. If you want to use 3-bit binary, then you can just use 3 B. So 1 0 0, and you can use whatever bit number you want. For an example, here it's a 2-bit, and then the number is value is equal to 2. And then you can also use unsized binary. So I mean, you just use this comma here, B, and then 1 0, the value is equal to 2, but the size itself is 32-bit, right? Unsized decimal, you can use 31 here, and then the value is directly defined, and then you can use hexa. So here in this case it's 8-bit hexa. So AF, and when you convert the number hexa here, you're going to get 175 in decimal. And then you can also use 16-bit negative decimal. For example here, minus 16, and then D57. So the value is minus 57. Okay, so and basic signals buses. So Verilog is a powerful language that you can use to specify multi signals and buses. So here's an example. So previously we are using just 1-bit input into A and 1-bit into B. Then if you want to change it into 8 bits, so you can easily do that by putting a bracket here and then a number of sex number. you want to use it. So for example here is from 0 to 7, which means 8 bits. Because if you start the count on bit 0 until bit 7, bit 0, 1, 2, 3, 4, 5, 6, and bit 7, then you're going to get 8 bits. So here, I mean, you're declaring both A and B inputs gonna be 8 bit size, and also you also declare the output up as upper as 8 bit size. So then you register, you declare the output as a register. The rest are the same here. Right? So the only thing that you need to change is the size. So that's why Verilog is easy when involve buses for the concatenate signals using the operator. So and this is how you can swap, the input for B here. So assign and then B is bit 7 to 0, bit 15 to 8. Okay, so let's see here, right? So first B doesn't have any value. So we're going to assign the A value into B. But if you guys look here in the order here, so we are swapping the half lower bit, we bring it to the front, and the half upper bit, we bring it to the back here. So that's why we see here bit 7 until bit 0 on the first half, and the second half bit 15 until bit 8. Right, so we assigning the value of bit A0 until A15 to this B value. And then after we assign the value, then this is how it looks like, right? So now B7 and B0 until B7 becomes all 1, and then B8 until B15 becomes all 0. And then if we sort it in order, which is the final result, we're gonna see when the value is swapped, right? Example here, it should be 1, 1, 1, 1, 1, 1, and then 0, 0, 0. And then now we are swapping it. So for B value, start with 0, 0, 0, and then 1, right? So this is how you can utilize concatenate assignment here. Right, then this is the example of a 7-segment decoder. So this is also you guys are doing it in lab 2, and you're accepting the BCD, binary coded decimal, which is a 4-bit to the input, and then the output going to be the 7-segment decoder, right, or the 7-segment signal. All right, so we can see here, I mean, this is the truth table for just output number 6 here, right? And then we can see how the circuitry looks like, right? So in and then these are and all those things, right? So these are how it looks like in the circuitry. So we can imagine that, I mean, it looks complex, right? If you want to design the BCD to 7-segment converter by using the gates itself, right? And then so this is the truth table, how we can construct this what do you call it, the 7-segment. So I've explained this in lab, right? So if example 0 here, I mean, all bits need to be 0 and just one bit is 1, because this is the 7-segment LED is active low. So all of the signal need to be 0 so that to light up the LED except bit 6, right? So bit 6 will be high, then it's not gonna be lighting up, right? So the rest of the LED gonna be light up, forming a 0 number. So you can follow the rest of the example to see how they construct 1 until F, right? And then so this is how the circuitry looks like. I mean, to construct the circuit for 0, right? Bit LED 0, LED1, LED2, right? So it looks really complex. And then this is how it looks like in terms of schematics. I mean, it's tedious. I mean, it's going to take, quite long time to construct the whole circuit. And then you can use the primitive gates in Verilog. This one, I think I've discussed it in lab 1. You guys also understand how these things being done. So it's tedious or it's hard to implement, right? And then you can also use direct mapping of Boolean here. And this is how the circuitry looks like, right? If you guys are using, you want to construct it by using the gate level, right? So you can see, I mean, like this is the assignment for output 6, which is the LED 6 of the 7 segment, this is LED 5 of the 7 segment, and this is the circuit construction, right? It looks really complex. That's why if we are using the RTL Verilog, then it's going to simplify our life. So just compare it, and instead of having all this complex circuitry, then we just simplify it just by using case here, right? So in this example, so this is a BCD to 7 segment, which we have 4 bits input, 3 to 0, and we have 7 bits of output, 6 to 0, and then we declare the output as a register Y because we are using always here. So this is a procedural assignment. To explain how the functions works, so it is in sequence, right? So always sensitive to input signal. So case input, we're going to check the input value. So if the input value is 0, which means it is 0, 0, 0, 0, then we're going to set the output as bit 100 to form 0 number. If the input is 0001, which is 1, then the output will be like this. So this is a setting to construct a number 1 in the 7 segment display, and then follows until F here. Right, so finally, this is to conclude the learning that we've done today. So what happened from Verilog code to FPGA? This is the flow. So the first one is the Verilog code. So this is the thing that we are working in the lab, right? So we are constructing our Verilog code, and then so we elaborate the code, so checking the syntax, expanding and threading instances. So we elaborate the code, checking if there is any syntax error or not, and then expanded Verilog code. So because a lot of what you call it built-in function being used here, so it's to simplify the developer or the designer, right? But then here to turn it into a circuit, so they will expand all the functions available, and then they will compile it. So behavioral description to get netlist or internal format related to hardware. Then they're going to change it into gate netlist because they want to construct the circuit within FPGA. So you need to have a definitions in terms of gate level. I mean, this is not being done by us, right? So for the designer, we just involved in the Verilog code. So the whole process here will be done by the software, but we just want to know the flow, what's happening after we click the compile. And then the synthesize to optimize the logic. So if they can reduce the logic, then they're going to cut it. So there's an optimization happening within the software itself. Then FPGA specific hardware, example logic elements or memory. So they're going to choose or assign which hardware that they need to use. Either it's a logic element, they also have a memory element within the FPGA, and then they do the plug, place and route, so fix the locations and wirings of all the FPGA, the hardware blocks for specific FPGA. So they do the routing. For example, when you click the view, right, the gate view, in the one that I've shown in lab 1, so you can see how the circuit being constructed. And then physical location of hardware and interconnect. So assembler produce the binary bit pattern needed to program the FPGA. So this is the final step where they change the code into the one that you're going to download in the FPGA board, right? Like the example I've shown in lab 3. Then you program the board. Right? So I think that's all the flow that we need to know. At least we know the flow. Right? We can explain what's happening in the first step, expanded Verilog code, get netlist, optimize netlist, right, until up into the programming configuration bitstream. Right, so I think that's all for today's lecture. So hopefully that's hopefully this lecture will help you guys to complete your exercise and understand this subject. All right, thank you so much. Bye bye.